Newton's second law of motion. An object doesn't change its velocity unless a force acts on it. Changing velocity can mean changing speed or direction. How does an object respond to a force when it's applied? Newton's second law identifies the relationship between acceleration, force, and inertial mass. When a net force is applied to an object, the object accelerates. The rate of acceleration depends on the net force and the mass of the object. The word net means overall or total. We will discuss this in further detail later, but for now, just think of sigma F as any force on an object. Sigma is the Greek symbol that generally means sum in math. So here we have Newton's second law. Acceleration equals net force divided by mass. The unit of force in the SI system is the Newton, capital N. Mass is measured in kilograms. Acceleration is measured in meters per second squared. Therefore, the unit of force, the Newton, can be found from the second law. If we rearrange Newton's second law to solve for net force equals ma, you can find the unit of force by just multiplying the units on the other side of the equation. Kilograms for mass, meters per second squared for acceleration. Therefore, the Newton is a kilogram meter per second squared. You can rearrange Newton's second law to suit the problem that is being solved. The version on the AP Physics 1 equation sheet is the best way to see the effect that force and mass have on acceleration. You can see here that the acceleration of an object is directly proportional to the net force acting upon the object. As the net force acting upon an object is increased, the acceleration of the object is increased. Inversely proportional to the mass of the object. As the mass of an object is increased, the acceleration of the object decreases. However, using F equals ma is sometimes better for problem solving. For example, if you draw a line downwards from the equal sign, you can see both sides of the problem. The left side of the equation is where we sum up all the forces acting on an object, which is why the object accelerates. The right side of the equation is where we determine what the object will do dependent on its mass. So this will show us how the object accelerates. The brilliance of Newton was linking kinematics to dynamics. His second law enabled the calculation of an object's acceleration by knowing the applied forces and the mass of the object. Acceleration is key to solving kinematics equations, but is not easily measured, whereas forces and masses are. A 0.4 kilogram toy car moves at constant acceleration of 2.3 meters per second squared. Determine the net applied force that is responsible for that acceleration. Alright, so first we list our givens over here, then we choose our equation, finally plug in your numbers and get 0.92 newtons. If a net horizontal force of 175 newtons is applied to a bike whose mass is 43 kilograms, what acceleration is produced? First, we list our givens over here, then we choose our equation, we solve it for a, so that means dividing both sides by m. So we have our new equation. Then we plug in our values right there, and we get 4.1 meters per second squared. A net force of 345 newtons accelerates a boy on a sled at 3.2 meters per second squared. What is the combined mass of the sled and boy? First, we list our givens over here, then we choose our equation, solve it for mass, which means dividing both sides by acceleration. We have our equation here, take your givens, plug them in, and we get 108 kilograms. What average net force is required to stop a 7-kilogram shopping cart in 2 seconds if it's initially traveling at 3.5 meters per second? This is a two-step problem. First, we list our givens. And we see that we're going to have to use kinematics first and then dynamics. So first, we're going to use the first kinematics equation and solve for acceleration. Plug in our numbers, because remember, if we're coming to a stop, that means the final velocity is 0. So we have initial velocity, we have time, we can solve for A, which is negative 1.75 meters per second squared. If this cart is moving in the positive direction, it must be accelerating in the negative direction in order to come to rest. Then we substitute that into Newton's second law, and we get a force of negative 12.25 newtons. Both the force and the acceleration are negative, as they're opposite the original direction of motion, and the object slows down. So in order to accelerate in the negative direction, you need a net force also in the negative direction.